Hi, my name is Noora Harris. In this video, I'm going to talk about my deep learning project that is speech emotion recognition. So first, I'll be talking about what is speech emotion recognition. It is the use of artificial intelligence to detect human emotions from speech signals. The SER models also use auditory signals such as tone, pitch, and pace to assess and classify emotions such as happy, sorrow, rage, and more. So this is my Google Colab code. That is the backend which I did. So as a first step, I'm importing the necessary libraries as you can see. And then I'm mounting the I'm mounting the Google Drive. So I got the dataset from Kaggle. The name of the dataset is Crowdsourced Emotional Multimodal Actors Dataset, also known as CREMADI. It has 7,442 audio clips from 91 actors. And it also includes 6 different emotions, that is anger, disgust, fear, happy, neutral, and sad. Here, I'm loading the dataset path. And in this step, I am just loading 5 sample files in the directory. Here I'm creating 2 empty lists. The first one is data, which will store the features extracted from the audio files. And the second one is labels, which will store the corresponding emotion labels for the features. Here I'm going to take the mean of MFCCs across time frames. The librosa.load function loads the audio file without changing its original sampling rate and also extracts 13 MFCC features from the audio. And in this part, I'm going to compute the mean of the MFCCs across the time, which will result in a fixed size feature vector. This function converts audio. This function converts audio data into meaningful numerical features for classification. This step is where the hybrid CNN plus LSTM model is defined for emotion classification. So in the CNN layer, I'm extracting spatial features from MFCCs and reducing feature map size to retain essential features. And in the LSTM layer, I'm processing temporal relationships in the extracted features. I'm also determining the size of the LSTM's hidden state. And in fully connected layer, I'm mapping the LSTM's output to class probabilities. And in this section, I'm adding a channel dimension to match CNN input shape and applying convolution, activation, and pooling. I'm also reshaping, I'm also converting the CNN output to a sequence format for LSTM. And then I'm extracting temporal dependencies and using the LSTM's output for final prediction. Here I'm loading the audio file and extracting MFCCs. And it will also print error processing file if to stop from any error occurring. Here I am loading a sample audio and its shape. So this step is emotion map where I am describing the emotions. as you can see. And this part is where the feature extraction happens. Okay, next we are going to exploratory data analysis part. So here I'm installing the Seaborn library for visualization and for creating plots. I'm also creating a data frame. This is the data frame, as you can see. It has 7,442 rows and 14 columns. This is a count plot showing the count of emotions in the data set. And now this is the visualizing MFCC's part. So here I am visualizing the MFCC of a single audio file. And this is a figure of the sample audio file. Here I am installing Scikit for pre-processing, classification, and evaluation. And also I'm using the label encoder class from sklearn.preprocessing to convert categorical labels. As here you can see there are 6 different emotions: anger, disgust, fear, happiness, neutral, and sadness. This is the features shape and labels shape. Here I'm extracting the prosodic features, that is pitch mean, pitch standard deviation, energy, and zero crossing rate. Also, it handles errors by returning a zero array when extraction fails. That is why I gave the printing code. So I'm loading the data set here and extracting the information from the file name. I'm extracting MFCC and prosodic features for selected emotions, and I'm combining them and returning a data frame with file names, emotions, intensity levels, and features. It also handles unexpected file formats and prints unique intensity values. So in this function, I'm calculating stress levels based on the emotion and intensity. I'm using predefined stress factors and intensity mapping, and returning 1 if it's stressed, and if the stress level exceeds 0.5. Otherwise, it's 0, that is unstressed. So this is the neural network model. Here I'm defining the feed-forward neural network for stress detection with 3 fully connected layers, that is ReLU activations, and a sigmoid output for binary classification, that is stressed or unstressed. I am training the model here and squeezing it to make the shape compatible. I'm loading the data function and calculating stress level using the calculate stress level function. Here the data set is loaded, extracting features and metadata into a pandas data frame named df. This is the shape. Here I am preparing the data for PyTorch and creating data loader for training and initializing the model, loss function, and optimizer. This is the main function to train and evaluate the model. As you can see, I am printing the accuracy, precision, recall, and F1 score. So I gave 10 epochs, and these are the results. This is the prediction part of the code. You can see the prediction. Predicted stress level is unstressed. And here I am saving the model state and configuration. This is the visualization part. This is the waveform which displays the audio signal's amplitude over time. And this is a spectrogram which displays the scale spectrogram showing the power of frequencies over time converted to decibels for better visualization. This is the correlation heat map. And this diagram shows the duration of audio files. Now we can move to the Visual Studio Code part. These are the necessary files and folders regarding my deployment code. So the app.py file contains a Flask application, defines the root and API endpoints for deploying the model. And the model.pth file contains the saved data, the saved state of the trained model, and includes its architecture and weights. The model.py file defines the neural network architecture. It contains the class or function that specifies the layers, forward pass, and the model structure. It is also used to rebuild the model when loading the saved weights from model.pth. And the utils.py file contains utility functions used throughout the project. The requirements.txt file lists all the Python libraries and dependencies. And the run.py file acts as the entry point for starting the server or application. So this is my website. Let's give a sample audio file. It predicts it as unstressed. Let's give another one. Neutral. So that also comes under the unstressed category. So that is all. This is my project, and it includes the front end and the back end. Thank you.